Arrow pushing mechanism shows the detailed steps of the reactions. So today I will talk about the EAS and NAS reaction. EAS stands for Electrophilic Aromatic Substitution. And here we have benzene and electrophile. So electrophile actually will going to replace one of the hydrogen on the benzene. So the product will be the substituted benzene. And the mechanism actually is always first step generation of electrophile. After generation of electrophile, the reaction will be between the benzene and the electrophile. So that's called the general steps. And the pi electrons from the benzene will attack this electrophile to form a intermediate. It's a carbocation here. Then a base will deprotonate this proton. You can see the proton bond with the same carbon of this electrophile. And then the base deprotonation will push the electron between the carbon and hydrogen back to here, form a pi bond. So we'll regenerate a double bond here. So the product will be substituted benzene here. So first step sometimes used also called de-aromatization. Second step also called re-aromatization. Now we'll talk about examples of EAS. First is halogenation. There are two common halogenation. One is chlorination, the other one is bromination. In chlorination, the benzene reacts with a chlorine molecule. Catalyst is the iron 3 chloride. Product is a chlorobenzene. Bromination just change the chlorine to bromine, and the product is the bromobenzene. Catalyst will be the iron 3 bromide. First step is generation of electrophile. So for the chlorination, the chlorine molecule, one of the chlorine atom will attack this iron in the catalyst. And then because iron has empty orbital, so form a complex. This complex will have a new coordinate covalent bond here between the chlorine and iron. Now chlorine here will be positive. So this will weaken this chlorine bond here. For bromination, very similar. Okay, will form a similar complex here. Then general steps we just talked about. For chlorination, the benzene will attack this chlorine because now this bond is very weak. So that's arrow pushing from the pi electron to here, chlorine, and break the chlorine-chlorine bond. Intermediate is the carbocation, and then a base can deprotonate this proton and push the electron back to reform the aromatic product, chlorobenzene. For bromination, very similar. So the benzene reacts with this complex. The bromine will be attacked by the pi electrons and break the bromine-bromine bond. And then intermediate is very similar, is that bromine, not chlorine. And then base will deprotonate the proton and push back the electron to form this bromobenzene. This is the arrow pushing mechanism of this chlorination and bromination. Now, another example of EAS is nitration. This time, you need a nitric acid and a sulfuric acid, and the product is a nitrobenzene. As usual, we will talk about the generation of the electrophile. Nitric acid, sulfuric acid. The lone pair of the oxygen in the nitric acid here will attack the proton. Basically, it's a protonation and formed this intermediate. You can see there's actually a water bond with the nitro group, and that's a byproduct, hydrogen sulfate. And this oxygen-nitrogen bond will just cleaved, and the water is a byproduct. This nitronium ion is the real electrophile for this nitration. Then mechanism will be similar. Benzene attack this electrophile, and then form this intermediate carbocation, and then base will deprotonate the proton here, form the product, nitrobenzene. If we only have a sulfuric acid, if we don't use nitric acid here, actually the reaction is called a sulfonation. Sulfonation, the product will be the benzene sulfonic acid. First step, generation of electrophile. again. So this time we only have a sulfuric acid, so 2 molecules sulfuric acid. One of the sulfuric acid will be protonated by the other molecule sulfuric acid. So follow a very similar arrow position, and you can see the water formed again here, and that's a byproduct. And the oxygen sulfur bond just dissociate, and then form the water as a byproduct, and the real electrophile for the sulfonation is a sulfonium ion. Benzene can react with the electrophile here and form the intermediate carbocation, and this proton will be deprotonated by base again and reform the aromatic structure, the benzene sulfonic acid. Now, last example of EAS is a Friedel-Craft reaction, include alkylation and acylation. In alkylation, the benzene react with the alkyl halide, most common chloride, and aluminum chloride as a promoter, and then product is alkyl benzene. Acylation, benzene react with the acyl chloride, and promoter is the same, aluminum chloride, and the product will be a phenyl ketone here. First step always be generation of the electrophile. For the alkylation, this example is actually isopropyl chloride react with aluminum chloride, the chlorine attack the lone pair share with aluminum, form a complex, then carbon chlorine bond just dissociate, and then form this real electrophile, which is a carbocation. For acylation, the acyl chloride react with aluminum chloride, lone pair of chlorine attack the aluminum, form this complex, and then carbon chlorine here bond will be just cleaved and form this acylium ion as real electrophile for the acylation. Following mechanism will be similar as alkylation. Benzene react with the electrophile alkyl, that is actually the carbocation, and then pi electron attack this carbocation to form this intermediate, another carbocation, and then base will deprotonate the proton again. You can see same pattern, and the product is the isopropyl benzene. Acylation mechanism, after generate this electrophile, benzene will react with this electrophile, the acylium ion, and then intermediate is similar, another carbocation, a base deprotonate the proton again, and then form this phenyl ketone. So they are all Friedel-Craft, but the products are different. Alkylation will form alkyl benzene, and acylation will form a phenyl ketone. Now, next we'll talk about NAS. NAS stands for Nucleophilic Aromatic Substitution. And we need a nucleophile, and that will replace the leaving group. Alg means leaving group on the benzene ring. Most of the time, you need an electron withdrawing group at ortho or para position, or both. And so the product will be substituted benzene again. Okay, just the nucleophile replace the leaving group. Let's look at the common mechanism. Nucleophile actually will attack the carbon bonded with the leaving group here and push the pi electron here between these two carbon to here, to this carbon. And since you will have a negative charge on this carbon and you have electron withdrawing group actually will stabilize the negative charge because they will reduce the electron cloud here. This have another resonance, just to push the electron to here and push the pi electron to here. This can also be stabilized by the other electron withdrawing group if you have electron withdrawing group here. So you can imagine you push this negative charge to here, push to here, and break that pi bond, you will have another negative charge here. So that's why if you have another electron withdrawing group on this ortho position, and the reaction will be even faster. But you don't have to. So now, second step will be the negative charge, the carbon anion, push back, kick off the leaving group. Product is substituted benzene. We will have two examples in slides here. First is this paranitrile bromobenzene react with the methoxide. What that is a nucleophile, and reaction needs heat. And then product will be the anisole. And the other example is actually leaving group is the chloro group here, and nucleophile is a methylamine. And this second example also have two electron withdrawing group, two nitrile group. So nitrile group is one of the most common electron withdrawing group. Let's look at the mechanism one by one. First, for the first example, nucleophile is the methoxide. It's a nucleophile. This will attack this carbon, and then you can see push the electron to here, and then break this pi bond, and negative charge here will be stabilized by the nitrile group here. Second step, this carbon anion will push back and kick off the leaving group. Product is this paranitrile anisole. Second reaction, you have two nitrile group. Supposedly this reaction could be a little bit faster, but the leaving group is chloro though, so it's hard to compare. So methylamine will attack the lone pair on the nitrogen, will attack this carbon and break this pi bond. Negative charge will be here, stabilized by nitrile group. If you draw the resonance, you can draw the negative charge here, also stabilized. Now, second step is the negative charge push back, kick off the leaving group, form this intermediate. I call it intermediate because it's not final product. You do need to depronate the proton here because you want product as neutral. So you need a base, depronate a proton, and then the final product is a neutral substituted aniline. So that's all the example of the EAS and NAS mechanism. And to summarize, the EAS is the electrophile replace the hydrogen on the benzene, and the NAS is a nucleophile replace the leaving group. Okay.